Okay, so I think it's, let's say, exact time, 9 o'clock. So good morning, and welcome to the second day. And for you guys, we have a very nice talk, basically, right, prepared by Dr. Jeorge. And Dr. Jeorge actually is very well known speaker, right? He has given talks at many places. He has a long bio in his sort of the slide set, so I'm not going to introduce too much on that part, right? With that, I would like to actually invite Jeorge. Jeorge, please.
Thank you.
Thank you.
Good morning, everyone. It is a pleasure to be with you today. We are indeed in very exciting times in the semiconductor industry, and in particular, the test and measuring industry. I have been around for 40 years in this industry. My career started when it was 5 microns, PMOS and NMOS. And I'm sure some of you here today go back at least 40 years. And I'd like for you to raise your hand. How many of you are here 40 years or more? Look at them right here. These are the veterans. They've been around, and it's been fun. But it seems like the fun is just getting started in this industry. I'm not going to go through my bio. I've been around for some time. But I want to start with a couple of quotes from Joel 2025. The whole ecosystem is changing, they're saying. It's being transformed due to this AI era that we're getting into. Data center processor market will more than double from today in the next 3 years to about $350 billion in semiconductor revenue. Just the GPU and the data center market. But also, interesting, along with that, the ASP, the average selling price for these devices, will also keep growing from about $3,000 a piece to about $28K by 2030. That's huge, which means no scrap. We got to help them, right? We have to help them. No scrap, because we cannot be throwing away these dies. It's no longer the case of IoT devices, even smartphone type of devices, where we could afford perhaps a few dollars of a scrap per unit. And the other thing that's going to happen here, we see new companies that are hungry for this business. And they want to get a piece of the pie out of NVIDIA, AMD, and Intel, the usual suspects, Google, AWS, and also others that we call hyperscalers. So these trends are indeed making this growth to $1 trillion. So what test challenges, what test opportunities, and why this is an exciting time? If you look at what it was when I started my career 40 years ago, it was basically nothing compared to where we're going. So really, you see, we have seen microchannels decreasing in size. I told you I started my career at 5 microns, PMOS and NMOS. They went to CMOS. And now we're in the Armstrongs. Clearly, that's enabling a large set of new test challenges and also enabling new opportunities for us. Back in late 1970s, first microprocessors that made it AIM-65 development system, 6502 developed by MOS technology. Anybody remember 6502 microcontroller? Those were being around for 40 years. That's what we started learning about machine language and programming, assembly language. And today it's all prompt engineering, right? Even if we know C and C# and all of that, prompt engineering that generates the program. So there's a lot of changes going on. So we got to keep pace with that. And indeed, as you can see, even though we did do, back in the 80s and 90s, multi-chip modules, different technologies. So this right here was a 3-chip, multi-chip MCM, and it had a DSP, it had a CPU, and it had an analog. Does that sound familiar? Different technologies optimizing the function of the node for a specific function and putting it together as chiplets today. It's happening. So it's almost things like deja vu, going back. But the challenges today are even orders of magnitude more than we faced in those days. We didn't have chip-to-chip, die-to-die interfaces like UCIe back then. We didn't have a stacked 2.5 3D type of things. This is new. Therefore, we got to now talk about what is it that is driving the test industry into new opportunities and new test challenges related to this thing called CoWoS, CoWoS, chip-on-wafer-on-substrate. That is new to us, relatively speaking, although it's been around for a few years, is now coming to prime time in 2025, 2026, 2027 to 2030. So the vectors are all aligning. As you can see here, identify 4 specific trends that are important to us. Number one, right here. We're moving to advanced nodes related to 1 nanometer. It's happening now. You see the timeline. It's now. Therefore, companies in this space, computer space, they can do more advanced chip, put into the radical limited size as much as they can, and the number of die per wafer is no longer 100, 200, it's maybe 10, 20, 30, because the chips are very big. We got to deal with that specifically on power thermal dissipation, which is a challenge I heard speaking in the last 2 days in the breakout sessions we're having here and the specific forums. The other vector that is aligning this industry, number 2, is heterogeneous integration. My topic this morning to make us aware of that situation and the test challenges there. And I already mentioned the rise of vertically integrated hyperscalers who want to do their own chips. Therefore, they're hiring a bunch of engineers, and they're innovating and doing things differently to a certain degree and driving the industry as well. And last vector that I want to highlight is adding co-packaged optics for the reasons that we have recently identified in various forums. Power consumption gets less, you get more bandwidth, you get more higher speed, and there's many benefits to that. So with those vectors aligned in the right direction, we see that the complexity is increasing. You got not only bigger chips, but we got this heterogeneous integration. That gives us with 3 specific areas. Require more effort from design. So EDA. We got our friend from Siemens Synopsys in the exhibits. They're coming up with new engineering to test to production type of tools that will make it more efficient, because engineering and engineers are scarce in this era that we're getting into. So the other thing, as I mentioned, is advanced packaging and also the engineering effort to develop test programs. And we heard some discussions about AI in test development in the past couple of days. So this particular talk concerns with data center compute. Although I would like to talk to you about the other 2 trends, which is hybrid AI or HAI coming up at some point, or even electrification of vehicles on power semiconductor, very interesting subjects. My focus is really today is going to be in the compute side, which, as you can see from my ATE, total available market, TAM, is the fastest growing in terms of the number of ATEs. These numbers they're revised almost daily. So it's just a trend. They're revised almost daily because there's new news, new opportunities coming up related to data centers. So don't pay too much attention to the absolute numbers, but the trend is there, and that's what we're here to highlight. Hyperscalers will take a bigger space right here, and therefore they will ask for new things from us and demand, because they need to catch up in terms of the incumbents. I already mentioned the emergence of silicon photonics and these type of things, so I will move on. Recently, we have seen evidence that this CoWoS, or chip-on-wafer-on-substrate, and variations of it are really here. And you heard the announcement from NVIDIA on the Rubin system. If you look at their new rack, it will have the equivalent of these many, hundreds of GPUs, the many thousands of HBMs, and all the capabilities that you can add in terms of compute power. We're talking about significant compute power. Not only there is power requirements coming to the rack, but power requirements coming to the actual devices themselves. Without going into a lot of detail, you can find this in the internet, but it's a nice summary that basically tells us the plans related to NVIDIA's Rubin and Rubin Ultra coming up in a couple of years. About 4 chiplets, going to 8 chiplets. And the main point I want to highlight here, you got this variation of devices. You got GPUs, You got the HBMs going to different type of HBM, stacking up 8, 10, 12, in terms of stack up HBMs. And you got CPUs as well. You got I/O. The I/O is being partitioned on the side, so to speak. So it's a different chiplet. And the other thing we see here is these new things called die-to-die interfaces like UCIe. So in addition to that, we got CPO. This one has 36 optical engines all around it. You see the little squares around it. And these now bring optical type of test challenges, as we have heard, and we see it all the time in the next few years. This is now then putting us into the fact that we had to test electronic IC chips and photonic IC chips, and in some cases, they're bonding into the same wafer, like the global foundries type of processing. In the case of TSMC, you have an electrical or electronics IC and a photonics IC put together, going through different processes, and eventually make it into a switch. First, the switch, not necessarily the GPU, because the switch, you got a bunch of interfaces, high speed, and that's an opportunity that is immediate for this type of packages. AMD has also announced the same type of things as being in production already. So bottom line is here. It is here, and this brings one, in my opinion, I don't know about you guys who've been around for 40 years. I'm excited. This is really, we needed this. It was getting a little bit boring the past 3-4 years after the mobility era kind of wound down. But now we got some energy going, and we see the fact that the era of complexity for monolithic to chiplets devices is indeed here. So we got to roll up our sleeves, and we're doing that and solve some problems. So the first thing I want to highlight is the fact that this thing here, called CoWoS, chip-on-wafer, has a lot of opportunities for failures in terms of possibilities of faults. And I want to talk about that a little bit more in the next few slides. And if we don't address this chip and bunch of interconnects and all of that before we put it into the package substrate, you got $30,000. What is it, $28,000 ASP going up? Call it 15,000, call it 10,000. It's huge. So you see, it gets expensive very quickly as the chips grow. So there's quite a few things to be concerned in this era. So let's talk a little bit more. First of all, let's just say that the definitions, we all need to be calibrating. Quite frankly, sometimes we talk about single-layered die, and what we're really referring to is single-layered CoW module. So we got to get calibrated. What are we talking about? Single-layered die or single-layered CoW module? I'm going there a little bit more because sometimes our language is not necessarily the same. So as an industry, we get to get calibrated. There's different variations. TSMC recently introduced what they call COP, P for panel. And let's not get confused with the panel when you go to the actual PCB in the system. That's a different panel. What they mean is replacing the round wafer interposer with a square, maybe silicon, maybe a different material. In fact, there's different materials, so that we don't have wasted area. You see all this gray area around the silicon interposer is wasted. We don't want to do that. So they're introducing this panel form, and this is something that is also happening. On top of that, NVIDIA just announced that they have a new technology that they were looking at called CoWoP, chip-on-wafer-on-platform, PCB. Let's get the terminology correct. Let's calibrate ourselves. Okay? That's another thing that TSMC, so no one can go wrong with CoWoS, which is the subject today, but it looks like AI giants such as NVIDIA are now planning to switch gears. So more innovation will be needed to test that type of devices by perhaps 27, 28. So back to the definitions. We've seen this several times flying in the internet, perhaps in the conference here. But you got the opportunities here related to failures on the stack up of the HDM. You have a multi-floor building, so to speak, of high bandwidth memories happening here. They get connected to something called a logic die at the bottom, which controls the whole stack up. And on top of that, you have these compute devices with some I/O that get connected via something called microbumps, which are very tiny, very small, and not necessarily probable with the current probe technology. And on top of that, or below that, you got to solder it at some point to the substrate. So you got opportunities. So I ask you a question. So even if you had a non-good die and a non-good single HDM, assuming they're good, perfect, and you were to now put in here as a stack up, and then on this, and then with all those macro bumps, and then all those vias, and then on this, and then the substrate, do you think you would be feeling that you have a non-good assembly at that point? Or would you wonder what's going on? So single non-good die may not be sufficient. We may need absolutely both. And the hypothesis I want to present here is that we do need both. We need both the single-headed die testing as well as the module testing that is called CoW. But that's right here. This is exactly what needs to be tested, and there is challenges there. Why? Because, as you can see from the bottom, there are bumps. It's a probe issue. It's a probe. It's not a handling issue. It's a probe issue in terms of the prober. And the prober today can handle radically limited devices, die, but not necessarily multi-die chips in the same space that today is being handled for the single die. So prober is something that needs to be upgraded. Then we put it into the pack, the substrate, we call it on-substrate. Okay, first of all, we see this picture like this, but really in reality it's like this. The compute die, the height, is the same for all practical purposes as the HDM stack. And what happens is they grind it. There is some planar software grind it and make it look almost planar. So when we see those little BPUs, the little die, it's misleading. They're really, roughly for practical purposes, the same height. Okay, why is that important? It's not necessarily important for test, but it's important to calibrate what we see in terms of what these packages look like. So it's more like an academic statement here, how it really looks like in terms of the pictures. All right, so let's continue. That's a point there. Here it is. So why is this an exciting time? Because, as I heard in a talk yesterday, a panel of, the big giants and data centers, the ones that buy all of this, the Microsoft, the AWS, they want non-good everything. Non-good everything. Non-good die, non-good module, non-good socket, non-good board, everything. So that means testing intensity is increasing, and that's good news for all of us in this forum, in the test and measurement industry. It's good news because there is more test insertions. So when we talk about single-headed die, first of all, the wafer, right? Not too many die, maybe 20, 30, depends on the size. Then you get some yield, and then what happens? You put it into a CoW, right here. You may have 1, 2, 3, 4, 5, we don't know. And then the orange is the HBMs, the stack up, not the same color in this picture, but that's that. Then are we going to test this insertion here called CoW module wafer test with the interposer? It's not clear that that will be a test insertion. It could be, but imagine all the power that is needed. How many GPUs are there in HBM? It's a thermal challenge. Just to provide a current, just to do the cooling, that's a challenge, and probably the biggest challenge we are facing now in terms of this industry that we got to solve. Yes, maybe we can throttle the current into a device and still be able to test it, but as I heard also on the panel, hey, we got to have the test as much as close as possible to the mission mode as in real life. So challenge is there. And then what happens when it's singulated? Then here we go. And this is an issue here. The test cell, because it's a probe issue, right? It's not a handler issue. You got to probe. Cannot today, most probers handle that size of a module. So that is an inflection point that needs to be addressed. And the question becomes, is this last step, when we put it into the substrate, a functional test or an SLT test? That MCN I showed you in the first slide, back when I was a product engineer at Rockwell, and all those challenges we had then of multi-chips, we went ahead and tested non-good die. We put it into an MCM, 3 of them, and then we didn't have enough pins to test every one of them again. So it was a system on a chip, in a way, on an MCN. So we did a quick functional test on Jeorge, and we did this parametric. Hey, everything is soldered correctly. It was assembled correctly. And then we went to a system-level test. It was actually a system-level test, testing those chips as modems. It was a system-level test. So where's Harry? Where's Harry here? Anybody see Harry? I don't see him. The lights are off. But he's talked about SLT, and we know that that's an area where we need to keep an eye on. Here we go. What's the difference between these two slides? The difference is this round interposer wafer being replaced by a more area-optimized panel. This makes a COP, as in Paul, or panel. Okay. So that also, do we have probers that are square like this? Do we have equipment that can handle this? Is it different? Should we do something different? We're just getting started on this type of questions. And of course, some companies are getting ahead on that, others are falling behind, depends on their strategies. But again, it's here, COP. And this is basically the summary on those two type of trends. Round for interposer panel, and recently there's been talk about 310 by 310 millimeter type of panels. Remember, these are 300 millimeter diameter, and these are 310 by 310, optimizing the area utilization before it gets singulated. So the main point up to now that I want to rehash over here, more test insertions are possible. Opportunities that we didn't have before. We were talking about time compression in the test industry, less time. But now it's more time, total available market, because of this. So you see here, now we got to be concerned about this other type of test insertions. And by the way, we don't add co-packaged optics on the side. But the CoWoS continues, it's there, but you got now to deal with co-packaged optics. So that brings us to the point as we got to get calibrated too on the CPO definitions, and this is just for you to have it there in case you could use it in training some people. Sometimes salespeople also need to understand these things, they do, and also our engineers in the organization. So, but the point I want to make over here, if you look, in addition to the compute side that we talked already a few slides, you got this new type of blocks, some of which not only need digital, but they also need serial, SerDes, and they also need RF testing, perhaps even on the wafer level. I have seen some people saying, hey, I like to test RF at the wafer level for these optical engines at gigahertz. I heard about 50 in that range, 50 gigahertz. That's millimeter wave frequencies. Good news that we went through a millimeter wave challenges the past 5-7 years. So sure, we can test that. That's not necessarily a new challenge, but it's a challenge or a change coming on the optical side, and so on and so forth. So the test flow that typically you see on these COW packages basically has pre, post, and bonding opportunities for metrology. So I'm switching gears now from ATE testing to, remember, this is test and measurement, right? Test and measurement. So test and measurement also includes metrology. And I'm going to bundle into that automatic optical inspection, so-called AOI. So what this is saying here is that all of these steps come into advanced packaging, some of which, this is important, some of which utilize wafer-level processing equipment. And you know what happens in wafer-level processing at the fabs? We've been around for some time. You got metrology. Metrology is an integral part of a fab. In fact, the wafers come with PICs. Everybody remembers what PIC is? PIC? PIC in a wafer. Yeah, there's a process, control unit or something. I don't remember either. But there was PIC and PEC. All I remember was a little area inside the wafer, maybe three positions, where now metrology could come and measure the channel length, the threshold voltages, as a way to monitor how good the process is. Metrology. They're not testing the die. They're testing 3 pegs in different corners of the die to see if the extreme cases, the corner cases, are going good. So now we bring that equipment into advanced packaging, and we start doing interposers and vias, through-hole silicon vias, and all of that. You got to measure to see if the process is doing the right thing. Pegs, why not? It's the same type of equipment. In fact, look at Lam, look at Apply. They have whole business units addressing equipment for this. So metrology is an opportunity that is happening for different reasons highlighted in this slide. To produce a finished CoW before it goes into the substrate, and in between, there are opportunities to look at, hey, why not X-ray inspection of the bumps? Are they in the right place? You know, what's the deviation, the rotation, the angles, the height, the width? That's a good opportunity for X-ray inspection. So these are opportunities also coming to this industry in terms of test. And I bundle metrology and AOI with the test and measurement industry. You got 12 stack HBMs. This is the traditional HBM flow. Okay, we've been around for some time, and I'm going to go through all of it. But basically, you know, you go through a testing of the die in a tester, you package it, and there we go do package test. On HBM, you get this die, you go through a stack process, you stack it up, as you can see here, 12 of them stack up like a buildings. Then you go through all kinds of stresses and tests and all of that. There's some JEDEC standards, by the way, to access the test points on these stack-ups at the logic die. Remember, there's a logic die at the bottom. And then you go ahead and do dice singulation. But I want to pay attention, you to pay attention to the comparison between this slide and the next one. What's changed? The new thing is right here, this block. Notice here, no block for singulation, singulation. So now saying, hey, I need to have non-good everything, so I need to have non-good HBM stack before I commit it to a CoW package. So this is also happening. So in the memory side, we're going to see the situation in which we have to now deal with stack HBM testing. And this is happening now. Will be more important. So the question is, do I have a good non-stack of 10, 12, 8, whatever HBM? So this is an inflection point also coming up in terms of stack up. Call it sub-assembly test. There was a question yesterday, too, on the panel is, do we need to be concerned about sub-assembly tests? The answer is yes. Yes. You got 10, 12 HBM. How do you know the through-hole vias, the through-hole silicon vias are working? How do you know a logic die is doing the right thing? And then the macro vias and the interface to the GPUs. So that is happening. On the CPU, we got the situation here that if we're going to commit to 36 optical engines, we don't want to waste any of this. Very expensive, I already said that. So we got to be finding ways to test at every level so we can have non-good optical engine in this case. Non-good everything. I'm stealing somebody's term. I liked it. Oh, no, my friend. Okay. So anyway, that is indeed what happens there. So why am I excited? Why is this good times? Why is this optimism? Because we haven't seen this for many years, you know, and this explains to a certain degree why it's more and more important that we collaborate together to find solutions as an open ecosystem. Not one company can do everything. We need partnerships, and that's what the Teradyne, our philosophy is an open ecosystem, to be able to solve problems based on our expertise. You see here new test insertions. You see here opportunities for metrology, automated inspection equipment, and then all the way to board level test, system level test. This is TAM growth for us in this industry. I talk about one of the key challenges, and it's been a hot topic for the past few years and in this conference. How are we going to handle this much current on these packages? Not only at the wafer level, but at the die level at the COW level, at the SLT level. Currents is going up, and they're deviating from the normal, quote-unquote, normal curve, exponential curve here, which you will follow if you do a curve fitting on the past few years. No longer the case. So the exponent is changing in that particular curve, and you see deviations now related to some of the latest chips being introduced. And of course, if you look at the system on wafer, like Cerebras and others are doing, it becomes a big problem. In fact, the question is as follows. Do we believe that the ATE and the SLT will ever keep up with the power requirements of these devices? Or if not, would it be cost effective? And is it practical even? Or should we look into alternatives? That is a question we're all pondering, and we need collaboration between the customers and ATC type of companies. ATC means adaptive thermal control, and of course, the ATE test cell. Liquid cooling is coming. There's talks about doing that. Well, I shouldn't say it's coming. There's research that it might be possible to put macro channels inside the GPUs and the switches and cool it down with macro channels with liquid cooling. I've yet to see that. That sounds pretty interesting. Imagine having little macro channels inside the die that bring water in there and cool it down. That sounds pretty exotic. And is it going to be cost effective? Is it going to work? Well, people are looking into that because of this issue. Air cooling is not enough. Direct cooling into the die. I mean, if you look at these systems, you got the GPUs, and you have a stack like this big of heat dissipation. Yeah, huge. Can we bring that to the ATE, to the SLT? I'm just talking about the opportunities here for innovation that we're all working. Because the bigger the die, the more layers, the more is needed in terms of power, current, and heat dissipation, and all of that. No more points over here to really bring up to you. It's just re-illustrates the issue of power and ATC management as perhaps the biggest challenge that we have seen for a long time. Yes, there's other challenges, but this is by far. And why? Because the compute power, not power as in current and voltage, but power as in compute power, you know, teraflops compute power, is increasing over the years, you know, from, you know, even all the way to 40x if you look at system on wafer, like the Cerebras, and perhaps even the Tesla that we have seen in the industry. So this bigger and bigger, you're talking about 2,500 watts, 2.5K watts, that's huge. Going to 4, yeah, it's just big. So basically the message here. And what that means is you have to watch a current being provided by the tester. And you know, there's a rule of thumb on how much the tester should bring. So if we take a rule of thumb that says maybe 2.5 times the device required current, we need to be in the 10,000, that sort of thing. So fun times, and obviously we keep working on that as well in the industry. Or maybe we do device throttling, power throttling. Maybe we don't apply all this current. Maybe we throttle the amount of current. You know, it's sort of like you know, slow mode, but you can still test, boot up the device. Maybe you can still do mission mode, but in a lower current environment. I'm not an expert, personally, I'm not an expert on this, but some of you are, and that's a possibility that perhaps makes sense, but our customer may not necessarily like this, may not necessarily want this, because you know, they want to see the real life type of application, non-good die, non-good COW, et cetera. But this is a possibility as well. We heard different speeches this week too on Interconnect. And the one trend that we need to be aware coming up here, and you know that, most of you, is hybrid bonding. So instead of, look at here, instead of having these bumps to be the interface between a chip and an interposer, for example, or RDL, There's nothing there. See, chip to chip, there's nothing there. What you have here is copper to copper bonding, okay? And that's called hybrid bond pitch. That allows us to get down here into the sub 10 micro very soon. It happens. But there is other considerations here. We cannot probe this. We cannot touch down on this. So we got to see what other implications this brings to test and probe technology and that sort of thing. But that's a trend happening. We're not quite there yet. We're primarily here. But there's new materials being investigated to bring us less than 10. In the meantime, we are now dealing with micro bombs. They're called bomb I/O here, or ball I/O. And this is more in the 50 to 40. So 40-ish micrometers is about right in the case of the current technology for COW or COP, as we discussed. And of course, then we go into the stack. We go into bigger balls. But this is a trend here to watch. Copper to copper type of interfaces, perhaps new materials. And the challenge is related to contacting. We'll probably bring some test points anyway. But just be aware. That is something happening too, that is another vector, so to speak, that is aligning with the requirements. And this view explains the difference between solder bombs, you see the range, micro bombs, you see the range here, and then going below 10 or so, you got to go with this copper-copper hybrid bonding situation. Actually, yesterday we had a very good talk by Andrew. Where's Andrew? From Marvell, I think it was, on silicon photonics, and he had very good set of slides. So if you missed that one, you might want to get and retrieve that one. This here is kind of a summary, but he had a really good presentation that I encourage you to download on the whole silicon photonics challenges. But the main point that he was bringing up, alignment. You got to align. The tolerance is very small. The rotational alignment of the prober, so to speak, you need a probe to inject the light into the wafer, and there is different techniques to do that. So the open ecosystem strategy that we at Teradyne have, it means we can work with different handlers and prober companies. Recently, we released an announcement. We have a dual-sided probing with Vicontex out of Germany, and that is one way to solve these alignment issues. So you got plenty of information on this. I just want to highlight. On top of the COW, you got COW CPO, and now we have to bring optical to the ATE. And the one thing that somewhere in this slide, and I'm going to bury myself on the slide, but one thing that shows here is the test cell footprint. You got all this optical equipment now, right, that you need to bring, and they're rack and stack. And the volumes are still low. So at some point, when the volumes pick up, we got to bring the rack and stack inside the tester head and be able to reduce the footprint. Because today, you have to have an extra cabinet. And we know our friends at TSMC and GlobalFoundries, they don't like big tech cell, right? Takes footprint, space, in every direction, power, and all of that. So the big challenge here, somewhere in this slide, is reducing the footprint of the tester cell. So moving right along, it's just you have this in your package, just instrumentation type of requirements related to optical primarily over time. I did mention about the test cell already, but there's some requirements somewhere related to other pieces of equipment, specifically serial interfaces, laser sources, wavelengths, and fiber types that we now need to be able to learn and articulate. And then die-to-die interfaces, like UCIe. People ask, UCIe is very sensitive. I'm happy to see that UCIe Standards Committee solicited the inputs from the test industry. Not too often done, but we were giving inputs. How are we going to interface to UCIe, being millimeter distances, and being able to not damage that interface? So people are thinking, as shown in this chart, to be able to have a translator, an active die, which is the one in pink, either in the top, in the middle, at the bottom. Just looking at different ideas. So you can take the PCIe interface from the tester, go into an active active layer, call it a translator, then you go UCIe and back, right? That might work. And you're gonna see this type of UCIe interfaces definitely in 2026, and then go and beyond as the standard is pretty much there. The next 3 slides, I'm just gonna hit the key points, summarize the challenges as seen by the IEEE Heterogeneous Integration Roadmap Committee test. I am co-chair of the HIR, IEEE HIR. Anybody here from our test chapter on the HIR? Here we go. We got Ira here. Do I see? Who is raising the hand here? I don't see. Yeah, so you see some member up there. So this gentleman here, we meet every month and talk about what's next in terms of test challenges related to heterogeneous integration. So any one of us, you can ask questions, but there is a free chapter download. If you haven't seen it, I give you the resource right there. You go there, you download several chapters from packaging to tests, all related to heterogeneous integration. It's kind of like good reference to have, and all of us test engineers and product engineers and business should at least have it handy as a reference right there. The last chapter, the last release was in 2024, so it's pretty much up to date. Non-good everything, non-good die, non-good interposer, and non-good COW, non-good stack up, and we talked about the things already, so it's like a summary. And then you have the whole signal integrity. We talk about UCIe, PCIe interfaces, and there's standards, of course, are helping us with this. The TSB interconnect, we already discussed that, right? The through-hole silicon vias. They need, perhaps metrology will help there. Metrology, right here. People are asking, how do we take care of that? You got probing, 3D stacks. So we touch on all of the things, but you got some more detail here extracted from the IEEE Heterogeneous Integration Roadmap, which you have a reference. So again, I repeat, try to get yourself a copy, a digital copy. It's a PDF that goes through all of this in detail. And I'm about to conclude here, and this conclusion basically highlights the need to be flexible in the next few years. All we know that the time is increasing. That's good news. Exciting times. Let's go enjoy the party, so to speak. But we also know complexity is increasing at different test insertions. It's an inflection point going on. So let's be flexible. We don't know yet if it's going to be all to the wafer level mission mode testing, shift left, maybe die test, maybe COW test, or everything. Because we don't want to throw away a 30,000 ASP, solution at the data center. So let's be flexible. So if the ATE can catch some disagreeing, some failures, at some point it doesn't become economical, introduce SLT. At that point, you see, you plateau with ATE, so SLT will find other failures, other faults. So the whole idea here is that we are flexible and we find a way to have some cost modeling, and every company will do their own things, that says, yes, I should go to SLT because it's more economical. I can do more fault coverage, or not, for the reasons related to the economy or the quality on the trade-offs. So clearly, if you look at test time and test cost and quality, if you are SLT, you get more coverage and ideally at a lower cost than if you keep just trying to put more into ATE, then we'll never actually detect those failures. That's what this is saying. So flexibility is key. Let's have an open mind. Let's debate, what may happen, what may not happen, but let's be flexible, which means that we got to also be thinking about data sharing between test insertion, shift left. AI may help us this in terms of bringing AI agents that can be motivators to companies to share data, because AI without data is nothing, right? We got to train a model, and to train it, we need data. Data. That's how we train the models. And to have data, we have to share the data. So maybe there is a motivator coming at some point if we can show value to our end customers who have the data through the whole process. So what can I tell you? It's exciting. AI data center computing performance requirement has enabled new heterogeneous packaging, more than more, and is bringing new opportunities for all of us. It's a complexity factor. There is metrology type of opportunities in every case. New test insertions, you have it listed over here. There's more. So let's go get this and win these markets in the next few years. And of course, let us keep working together and collaborate. With that, I want to thank you for your attention.
Hey, George, wonderful talk, okay? This is Stepan Chakraborty from Renaissance Electronics. The question is, the cost of test, you had some slides at the end, cost of test is skyrocketing. And typically, in chiplet level, a typical number